young researcher. I just want to motivate the young guys for research. So I start to begin. This is our research about development of biosensor. So this is Professor Anton Turner. He's a well-known researcher in biosensor. So he's the one have a patent for development of this. You know this for device of diabetic. It saves millions of lives every year. So every year is like $13 billion this industry. So for our research, we try to publish our work in the journal, it's a high reputation journal. So the rejection rate is about 80%. So we just try to do our best. So the teacher said it's better to pray because they almost rejected the research. So after 3 months, because we are working maybe 2-3 years in development of this sensor and to do the real application. So when we see the teacher, our teacher computer about acceptation like R, it means rejected. So it was really work day and night to achieve our aim. After that, they asked us some questions about our publication. So finally, after 3 months, they accept our publication because we did really deep research and we applied it using the nanomaterial. So after that, we received several invitations for conference. So because of the limit of research, so we choose the Omnic because we found it more suitable, and also the design, also the communication. You can see here several emails I changed with the guy. He was disturbed, and every time less than 24 hours he replied our message. So my topic is development of high sensitive electrochemical genosensor based on multiwalled carbon nanotube-chitosan-bismuth for gene detection. So our aim is to detect the gene. So this house, you know, is a classic method for the detection, immunological, polymerase chain reaction, and also culture-based method. All of those methods have some problems. So some is about the time, some about is like a polymerase chain reaction, about the inhibition of PCR product, the stress of antibody depend on physiology of the organism. So the new method should be more sensitive, rapid, and also low cost. So this is the some development method. Until now, this is the future of the biosensor. So for us, we focus electrochemical method. So this is a combined electrochemistry and the nanotechnology. So it's a broad application. You can apply in environmental science, microbiology, food safety, molecular biology, toxicology, chemistry, and the advantage, it's rapid, low cost, and high sensitivity. So this is our equipment. The left side is an electrode system. The right side is like our computer, so it's not take too much space. So this is interpretation is very easy. You don't need a special background. You just need to detect the peak position and the peak intensity. So this is all. So our experimental design by nanomaterial genomic searching, these bioinformatics guys help us too much. Probing primer design, bacterial strains after PCR, amplification of specific gene, construction of genosensor, fixing probe, detective probe, nanoparticles. We did some optimization, of course, and time, temperature, incubation. And we use the real bacteria for the detection. So we did some artificial contamination, and we continue. So we did the searching for gene and the NCBI, and also we use the Sigma. It helps us about the genome selection. This is a synthesis of nanoparticles. We use three kind of nanomaterial. This is lead sulfide nanoparticles. We just use the lead nitrate, had glycolic acid. So after that, we add sodium sulfide, is a critical point, and nitrogen. So we got the nanoparticles. And we use the acid group to cover our nanoparticles. But you should pay attention about the pH, the temperature, the liquid nitrogen, the preservation, because it can have some problem during precipitation. So this is our nanoparticles. It's like lead sulfide colloid. This is the good quality one. So this is the transmission microscopic image. So when we got our nanoparticles, so we cover with acid group, and after that we use the cross-linker, and plus our oligonucleotide from the company already have amino group. So this is the figures. So for your understanding, we cover the nanoparticle with some complementary DNA sequence of DNA. This is our gold electrode. The gold electrode, we use it as a fixing surface. So we need to do several experiments to achieve to clean it very well and do the fixing process. So this is our ACH group, and attach it to our complementary sequence. So this is our hybridization. So our aim is to hybridize to specific gene. And after that, we detect in our equipment. As you can see, this is a signal. This is crossing chemistry. This is a resume of our experiment. This is fixing in the yellow one means gold. So this is a fixing process. We do some chemical treatment. After that, do some hybridization. The green one is our nanoparticles. So we put in nitric acid, and we do electrodeposition. This is the critical steps also, because sometimes you can work all your experiment. If you do mistake in electrodeposition, you just get your baseline. So for this one, we have nanomaterial, multiwalled carbon nanotube. It's showing our experiment have more, the conductivity highest than the normal gold. So after that, this figure you can see, this tree green is our nanoparticle when it's released. So when we release our nanoparticle, it's okay. We can detect it by our machine. This is the left one is some curve we made to see the conductivity. As you can see there, the gold, the carbon, the electron when they cover with multiwalled carbon nanotube, the sensitivity is increasing, so you should test it before. And when not using the carbon nanotube is the lowest, as you can see, the pink one. Another right side is the impedance spectroscopy. Is also we can show the C. The blue one, the straight line means that not showing any significant resistance. So when you cover it, it increases sensibility. This is our image. This is the scan electron microscopic. The left side is just carbon nanotube, and the chitosan also is very important. And another one is multiwalled carbon nanotube with chitosan in the bismuth. Bismuth shows us very good quality because it can attach to the released nanoparticles, and you can detect it. So this is the linearity of our experiment. It shows high stability when we cover our electrode with multiwalled carbon nanotube. So this is some optimization. This is temperature. We found it's 45 degrees, time is 60 minutes. And also the deposition potential, minus 1.2 volts. It's very, very important. Because if it's less, it can have problem for deposition. If it's more, it can destroy your nanoparticle. You cannot detect anything. So this is the experiment. We use different genome concentration, and you can see high sensitivity when you recover with your material. So we do the pure genome detection. Now it's the application in the genome detection. The pure genome detection, we use the kit for purification. It can show your DNA and you can detect it. So to do the curve in machine, we use it the kit for DNA purification, and this is different concentration of oligonucleotide. This is pure one from bacteria. You get your bacteria, after that you do your purification, you detect it. So this one is simple one. We need to go to the real one because the sample normally we get from the food or blood or clinical samples, something like that. This is the different biosensors. They are really relatively new. Is different research found some limit of detection is like 10 power minus 14 to 10 power minus 10. They use the different nanomaterial, but some guys they just do it using the synthesized oligonucleotide from the company because it's really hard to do it in real sample. But for our research, we try to go more. Some guys they start to use it also in the bacteria, in the real one. As an example, we can have the salmonella. Also, this method can detect the specific gene for the disease because, as we know, there are many bacteria that sometimes is not harmful, and we can spend money and time. So our method is about 10 femtomolar, the limit of detection. So we use with the different strengths. Our bacteria is Aeromonas hydrophila because it's well-known pathogen for human being. Also, it can cause fish disease and something like that. So we use also no target strain E. coli, the pathogenic one, and Staphylococcus aureus. We do also we design specific primer for the gene to try to amplify no target microorganism to see our test. So the figures show 1, 2 twists means yes, it means our target. Also our PCR primer, it cannot amplify it, could not amplify it. And we use these 4 and 5 is for Staphylococcus aureus in E. coli. It was not our target. And another one is DD water. As you can see, 4, 5, 6 is the signal is near the background. So detection real sample. First we tried the easy one, the water, using boiling method, different concentration. It gives us the PCR product, and also we could get the signal using the boiling method. So this is the signal. The last one is near baseline. We didn't consider as a signal. So we use application in real sample. It's like a problematic sample. Why we use problematic sample? Because in the reality, the experiment, we can get many problems. So we use the problematic sample because they have some protein or something like that. So in the application problematic sample, we did extraction of bacterial DNA from sample, and also the problem is inhibition of PCR reaction. As we know, we need to do purification very well, and also some inhibition the false negative. And we did, because it was School of Food Science Technology, we use milk, fish, and also vegetables. And according to the figures, we can see that we use the chloroform phenol method, and also we use a boiling method because it's very quickly method. We try to save the time. So we do centrifugation. This is the resume in buffer after lysozyme proteinase key, SDS to separate chloroform, and then after that we got our genome, and we use the direct electrochemical machine and also PCR to see. We do also centrifugation, boiling method. We just need to your bacteria, you put suspend in the water, and you boil it. After that, you chill it in ice. It explodes the bacteria, so you can get your genome. It's quickly method. And then we get our supernadant. Actually is a good method. So the milk sample is a problematic one. High fat content is really hard to separate the bacteria from the milk. So it shows here the PCR we could detect 10 power 6 to 10 power 4, and electrochemistry you can go to 10 power 1. But the boiling method, it cannot work because as we boil it, it can like flocculation, so everything's aggregate. So for vegetables, also we did electrochemistry, it show good sensitivity. Also we do PCR, also 10 power 3. And using also the boiling method, it was not so suitable for PCR. For fish, also we did the same, and electrochemistry also shows some signal, and also the PCR couldn't detect well the genome in the boiling method. This is our some part of our experiment extraction. This is our sample. This is, of course, in the experiment, sometimes you face problems. This is our problem in the beginning. This is our nanomaterial multiwalled carbon nanotube. Sometimes you have problem because of link with chitosan, but after that we found solution. We put in our supplemental material. This is our nanoparticles. This is, it's all. Okay, thank you very much.
Any questions?
Thank you for the presentation. Personally, my background on biosensor is quite limited, but one suggestion from me, it also like a question. I'll ask it as a question. You say that boiling method, there is disadvantage using milk, because if you boil milk, you form foams. But is that available that you use nitrogen, liquid nitrogen to burst the cells, or using sonication probes to your sample?
I got your point. If you use the sonification, for example, your bacteria is inside and the milk is together, you cannot separate because the bacteria is inside. It will mix. It will mix. So the method until now they use some special kit for milk, vegetables, something like that. But for us, we just want to we want our research, in our experiment we try to find some troubles, and several times we try it, and finally the final method, it could separate us with the cheap. It's a cheap method. But if you use for example the colony is near 100%, it will be detected by sensor. If it's not detected, it means all your previous experiment is wrong. You should set in the machine again. Yeah.
So indeed, bacteria when they will burst, they will mix with the milk.
Yeah, they mix. Yeah,
but,
we hope.
But the DNA of the bacteria, you can isolate it, right?
Yes, by phenol chloroform method.
Yes.
You can use sonification, for example. Yes, it's a good idea. Sonification. If, for example, you have your pure bacteria colon, You can just suspend in buffer or DD water, 5 minutes, and you can get it. And that's why 3 hours you can get your result in the sensor, because the surface of electrode is electron transfer process. You are going very, very, very sensitive. Yeah.
Yeah. So what about if you use nitrogen liquid?
The liquid nitrogen can also burst the bacteria, right? Because frozen, yeah, this is also is very good. It's very good. Of course, that way is very important for sharing the knowledge. It's very important for sharing the knowledge. We use the nitrogen for since of our nanoparticle. It was so near us, and we couldn't have this idea about using nitrogen.
Okay,
Yes.
I have a comment, actually, not a question. Liquid nitrogen, you cannot burst the microorganisms. You just freeze it, right? So you cannot really burst. You cannot release the DNA from the bacteria by liquid nitrogen. But the way you release the DNA from bacteria is that you freeze it and then you throw it. The membrane is going to be right? So that, is,
Yes.
not just simply spring for the liquid nitrogen. Because you store cells in the liquid nitrogen.
Yes, it's
So let me see. If you use liquid nitrogen, okay, it's like how to say? It's also a thermal. You can like a thermal shock. It's the inverse, because the boiling metal, you boil it and after that -20 back. Okay. If you use liquid nitrogen, for example, you can do the inverse. Yes. It's also a good idea. It's a good idea. It's a good idea.
Actually, one question. Grab the microphone so I'm going to ask a question.
Yes.
I probably missed some point. So you're talking about like a nanosensor. Right?
Yes.
Could you just talk a lot about the DNA isolation, DNA purification? So what was the goal of this nanosensor? Simply detect the amount of DNA in any kind of sample, or are you going to try some specific DNA sequence from certain microorganisms or anything else? I kind of missed that point. So what was your goal actually?
If our aim is to detect the gene or bacteria, this is what you want to say?
What was your real objective for this nanosensor? Just detect the DNA, the presence of DNA in the sample, or something else?
Yes. Actually, it is a DNA, because we use the probe like array. Some professor present previous. We use for this, but the same electrode we treat with multiwalled carbon nanotube, chitosan and bismuth. It could use also in the environmental science, like pollution, because the lead or cadmium and another heavy metals can be attached also. Yes. For our study, our aim is to detect the genome and the sequence. Also, another guys they use for antibody detection. You just need to have your synalyzer to keep the signal. But until now, the scientists trying to search more nanoparticle to get the more peak, like simultaneous detection, something like that.